In this video, we will learn how to find local and global maximums and minimums of a multivariable function. But first, let's review how to find maximums and minimums of a single variable function. So what are the steps for finding the global maximum and or minimum of a function f of x on the interval from a to b? That first step was to find all critical points. Now, critical points, if you recall, those are points where the derivative is equal to 0 or the derivative does not exist. Now, once we found those critical points, we're going to classify critical points as local maximums, minimums, or neither. And you may recall doing this using a first derivative test or a second derivative test. Finally, we're going to evaluate f of x at critical points and endpoints and compare values to find global maximums or minimums. So you will recall that for a global maximum or minimum, those could actually be one of the local maximum or minimum points, or those global maximums and minimums could occur on the endpoints of the interval. So that first step is locating critical points. And so we need to have a method to locate critical points of a multivariable function. So before, critical points occurred where the derivative is 0. And so what does that mean for a multivariable function? Well, what represents the derivative? The derivative is really represented by the gradient, which has the partial derivatives. And if each of the partial derivatives is 0, then that's going to give us a critical point. So our first derivative test says let f be a differentiable function with a local maximum or minimum located at r0, then it must be the case that the gradient of f at that point r0 must be the 0 vector. So if f has a local maximum or minimum, then there's going to be a 0 gradient or no change in the x or y directions. Okay, so we want to prove this statement. And the way that we're going to prove that statement is we're going to start by letting h be a vector. It's going to be an arbitrary vector. And we're going to define a function. We're going to call that function g of t. And g of t is going to be f of r0 plus th. And when we define that, that's going to be a path on the surface f of r through r0. Okay, so on the left side of my screen here, I have a surface I'm going to call f of r. And what we're going to do is we're going to take a point r0. So here I'm going to have a point, we'll call that point r0. And then I'm going to essentially define a line through R0. Okay, so the line through R0, that's going to be R0 plus t times h. And so if the red line there, R0 plus t times h, is a line through R0, there is a corresponding path on the surface say there, that corresponding path on the surface, that corresponding path is going to go through the point f of R0, and that path on the surface is going to be given by, in this case, g of t. So g of t is going to be the path on the surface. Now, that path is going to go through the point R0, and R0 is going to be a point where the local maximum or minimum is located. So here I've drawn it as a local maximum. So since f has a maximum or minimum at R0, okay, then what I really have for g of t is a single variable function, okay, and R0 in this case is going, or f of R0 is where the maximum of that single variable function exists. And so g prime of 0, right, which is going to be the derivative of f at 0, has to be 0. Okay, so I'm defining this function g of t, so I essentially can make this a single variable problem. Okay, and so if my multivariable function has a maximum at f of R0, then I should be able to draw a path through that point, and then there should be the maximum of the path through that point should occur at g of 0. And if that's the case, then g prime of 0 would need to be 0. Okay, well, now I'm going to apply the chain rule. So by the chain rule, if I take the derivative of g of t at t equals 0, we've already said that that derivative is 0, but the chain rule says that that derivative should be the gradient of f of R0 plus t times h, dotted with the derivative of the inside, R0 plus t times h. The derivative of that is just h. And of course, that's going to equal 0. Okay, that comes from the fact that g prime of 0 is 0. But this direction h that I picked, h is just a vector and it's arbitrary. So since h is arbitrary, okay, it could be any direction, then it's not the dot product that's making it 0. It must be that the gradient of f at R0 is 0. Okay, and this is going to show essentially then that if a maximum or minimum occurs, then the gradient must be 0. Okay, so that's going to give us our definition of critical points. Critical points are going to be points where the gradient is 0. Okay, so now I would like to do an example. Okay, I want to find all critical points of this function, f of xy equals 2 times x squared plus y squared, e to the minus x squared minus y squared. So I just want to find the critical points of this function. It kind of looks like a volcano. Okay, well, the way I'm going to do that is I'm going to find the gradient. So I need to find the partial derivative of f with respect to x. Okay, that's going to require the product rule. Okay, so the derivative of 2x squared is going to be 4x. And then I leave the exponential alone. And then I leave the 2 times x squared plus y squared alone. And I take the derivative of the exponential as e to the minus x squared minus y squared. And then I take the derivative of the minus x squared minus y squared, which is a negative 2x. Okay, so let's see here. I can factor out a 4x times e to the minus x squared minus y squared. What's left? Okay, so I've got a 2 times 2. That's going to give me 4 there. And that's where I get another 4x, just if you're wondering how I'm going to factor out 4x from each of those terms. Okay, so 4x e to the minus x squared minus y squared, that is the first term, so that gives me a 1. And then what I have left is a minus x squared plus y squared. So I'm going to set that whole partial derivative equal to 0. And that tells me that either x in this case is 0, or it must be that x squared plus y squared is equal to 1. Okay, so the derivative with respect to x is 0, either at x equals 0, or on that circle x squared plus y squared equals 1. Okay. Now let's look at the partial derivative with respect to y. This is going to be very similar. Okay, so taking the derivative of the first term, so taking the derivative of 2y squared, I'm going to get 4y. I've got my exponential. And then I'm going to leave that first term alone, 2 times x squared plus y squared. And the derivative of the exponential is itself times the derivative of the exponent, which in this case is a negative 2y. So this is going to factor out the same as last time. So 4y e to the minus x squared minus y squared, okay, times 1, and then minus x squared plus y squared. Okay, so when is this going to be 0? Okay, so that gives us two possibilities. Either y is 0, or x squared plus y squared is equal to 1. Okay, so now I need to find places where both partial derivatives are 0. So in this case, if x is 0, okay, then by necessity, I will need y to be 0 so that both partial derivatives are 0. So my critical points, okay, if x is 0, then y will have to be 0. Or the entire circle, x squared plus y squared is equal to 1. Okay, so those are my two critical points. Okay, so 0, 0, or x squared plus y squared is equal to 1, the entire circle. And so notice, essentially, I have infinitely many critical points. This is something that can happen. Okay, you might not just get one single critical point or a finite set of critical points. In this case, I have infinitely many critical points. Okay, one of them corresponds to the point 0, 0. In fact, you can plug 0, 0 into this function and you will get 0. Okay, so this is one of the critical points. It's hard to see, but that volcano actually shape, it dips all the way down, okay, and it forms kind of a minimum there inside that surface. And so you can see why 0, 0 is a critical point. There is kind of a minimum there. And then there's this cool local maximum that's going on, okay? Right here, this lip of the volcano around the circle, x squared plus y squared equals 1, okay? There, when x squared plus y squared is equal to 1, we have a maximum, Okay, uh, and that is a local maximum, or I mean, in this case, actually, it's a global maximum, but all the points on there form a global maximum. Okay, each one of those points on that circle is a maximum, and you can see that. So this is kind of a cool example because we have an infinite number of critical points, and not something like we had before where we would just have, say, a finite set of critical points.